Have you ever watched a figure skater pull in their arms and suddenly spin so fast they become a blur and wondered where that extra energy came from? Or seen a child on a merry-go-round speed up dramatically just by moving closer to the center and asked yourself what invisible force is accelerating them? What you're witnessing isn't magic. It's one of the universe's most beautiful conservation laws in action. A principle so fundamental that it governs everything from spinning skaters to rotating galaxies. Today, I'm going to reveal a truth that will change how you see every rotating object in your life, from the ceiling fan above your head to the planet spinning beneath your feet. The answer isn't what your physics teacher told you, and it reveals a deeper secret about how the universe keeps perfect mathematical accounts of every motion that has ever occurred. The mystery begins with a simple observation that defies our everyday intuition about energy. When a figure skater extends their arms and spins slowly, then pulls them in and spins faster, it looks like they're creating energy out of thin air. After all, kinetic energy depends on velocity, and if they're moving faster, shouldn't they have more energy? Your brain, trained by a lifetime of pushing objects to make them move faster, expects that speeding up requires adding energy from somewhere. But in this case, no external force is pushing the skater. No engine is accelerating them. No one is giving them a shove. So where does that dramatic increase in rotational speed come from? The answer lies hidden in one of Emmy Noether's most profound insights about the relationship between symmetry and conservation. In 1915, she proved that whenever the laws of physics remain unchanged under rotation, whenever there's no preferred direction in space, something called angular momentum must be conserved. This isn't just a nice mathematical principle. It's an iron law of the universe that governs every spinning object from electrons to galaxies. And the spinning figure skater is about to give us a masterclass in how this cosmic accounting system actually works. Picture the skater at the moment they begin their spin with arms extended. Their body possesses what physicists call angular momentum, a quantity that depends not just on how fast they're rotating, but on how their mass is distributed relative to their axis of rotation. When their arms are stretched out, their mass is spread over a larger area, giving them what we call a large moment of inertia. Think of moment of inertia as rotational mass. It measures how difficult it is to change an object's rotational motion. A figure skater with extended arms has a large moment of inertia, just like a heavy object has a large regular inertia. But here's where the magic happens. Angular momentum equals moment of inertia multiplied by rotational speed. And because angular momentum must be conserved, because Emmy Noether's theorem demands it, if one factor in this equation changes, the other must change to compensate. When the skater pulls in her arms, they dramatically reduce their moment of inertia by concentrating their mass closer to their axis of rotation. To maintain the same angular momentum, their rotational speed must increase proportionally. It's not that they're creating energy from nothing, they're redistributing the rotational energy they already possessed. This is where most explanations stop, but they miss the most mind-bending part of the story. The skater actually does more work when they pull in their arms. They're fighting against centrifugal force, the outward pull created by their rotation. This work adds energy to the system, but not in the way you might expect. The total energy of the spinning skater actually increases when they pull in their arms, even though no external force is acting on them. How is this possible without violating conservation of energy? The answer reveals something profound about the nature of energy itself. The skater's muscles do work against the centrifugal force as they pull their arms inward to convert chemical energy from their body into additional kinetic rotational energy. But this isn't obvious because the skater doesn't feel like they're doing work to speed up. They feel like they're working to pull their arms against the outward force. The increased rotational energy is a side effect of changing their moment of inertia, like getting a speed bonus from the universe's conservation laws. To understand this more deeply, imagine you're sitting on a rotating chair holding weights in your hands. When you pull the weights toward your body, you have to work against the centrifugal force trying to fling them outward. This work doesn't just disappear, it gets converted into rotational kinetic energy, making you spin faster. The universe keeps perfect books. The chemical energy in your muscles minus the work done against centrifugal force equals the increase in rotational kinetic energy. Every joule is accounted for, every calculation balanced. But the conservation of angular momentum extends far beyond figure skating rinks and rotating chairs. It's the fundamental principle that explains why hurricanes intensify as they shrink, why pulsars, collapsed neutron stars, can spin hundreds of times per second, and why galaxies maintain their spiral arms over billions of years. When a massive star collapses to form a neutron star, its moment of inertia decreases by a factor of billions. To conserve angular momentum, its rotation rate must increase by the same factor, creating objects that spin faster than kitchen blenders despite being more massive than our sun. The same principle governs the formation of planetary systems. When a cloud of gas and dust collapses under its own gravity to form a star, conservation of angular momentum requires that the cloud spin faster as it contracts. This is why most stars rotate and why planetary systems form in rotating disks. The same disk of material that gave birth to our solar system 4.6 billion years ago. The gentle rotation of the original gas cloud, amplified by conservation of angular momentum during collapse, ultimately determined the orbital motion of every planet, moon, and asteroid in our cosmic neighborhood. Even at the quantum level, angular momentum conservation plays a crucial role in determining the structure of atoms and molecules. Electrons possess intrinsic angular momentum called spin, and when atoms interact or chemical bonds form, the total angular momentum of the system must be conserved. This quantum mechanical bookkeeping determines which chemical reactions can occur, how molecules rotate and vibrate, and ultimately the behavior of all matter at the microscopic scale. The mathematics of rotational motion reveal beautiful connections between seemingly unrelated phenomena. A figure skater pulling in her arms follows the same mathematical principles as a contracting gas cloud conforming a star, or a hurricane intensifying as it approaches land, or a galaxy maintaining its spiral arms over cosmic time. The equation L equals I omega, angular momentum equals moment of inertia times rotational velocity, applies equally to spinning electrons and rotating galaxies, connecting the quantum world to cosmic scales through Emmy Noether's fundamental insight about symmetry. But angular momentum conservation also has profound implications for our understanding of time itself. The conservation law emerges from the rotational symmetry of space, the fact that the laws of physics are the same regardless of which direction we face. This connection between spatial symmetry and temporal conservation reveals something deep about the structure of reality. Time and space aren't separate entities, but are intimately connected through the conservation laws that govern all motion and change. The principle even applies to more exotic scenarios that push the boundaries of physics. Black holes possess angular momentum, and when they merge, the conservation of their combined angular momentum determines the properties of gravitational waves that ripple through space-time. These waves, detected by facilities like LIGO, carry information about the rotational motion of colliding black holes billions of light years away, allowing us to study angular momentum conservation in the most extreme environments in the universe. In everyday technology, angular momentum conservation enables gyroscopes to maintain their orientation despite external disturbances. Spacecraft use reaction wheels, spinning masses, to control their attitude by transferring angular momentum between the wheels and the spacecraft body. When engineers want to rotate a satellite, they speed up or slow down these internal spinning wheels, and conservation of angular momentum automatically rotates the satellite in the opposite direction. It's the same principle the figure skater uses applied to navigation in the vacuum of space. The conservation of angular momentum also plays a role in understanding Earth's rotation and the length of our days. When glaciers melt and water redistributes from the poles to the oceans, Earth's moment of inertia changes slightly. To conserve angular momentum, our planet's rotation rate must adjust, leading to measurable changes in the length of a day. Even major earthquakes can alter Earth's moment of inertia enough to change the length of a day by microseconds, a testament to the precision with which nature maintains her conservation accounts. Athletic performance in many sports relies on understanding and exploiting angular momentum conservation. Divers and gymnasts use the principle to control their rotation rates during complex maneuvers, pulling in their limbs to spin faster for multiple rotations, then extending them to slow down for precise landings. Baseball pitchers and ice hockey players use the transfer of angular momentum from their entire body to their throwing arm to generate incredible velocities. Even dancers use these principles, though perhaps unconsciously, to create the flowing, accelerating, and decelerating motions that make dance so visually compelling. The study of angular momentum conservation has also led to discoveries about the fundamental nature of matter itself. Particle accelerators create new particles by colliding high-energy beams, and the angular momentum of the colliding particles must be conserved in these interactions. This constraint helps physicists predict which particles can be produced and with what properties, providing crucial tests of our theories about the fundamental forces and constituents of matter. As we look toward future technologies, angular momentum conservation continues to play important roles. Proposed space elevators would need to account for the transfer of angular momentum between Earth's rotation and climbers ascending the cable. Fusion reactors must carefully control the angular momentum of spinning plasma to maintain stable confinement. Even quantum computers rely on the manipulation of electron and nuclear spin states, making use of angular momentum conservation at the most fundamental level. Perhaps most remarkably, angular momentum conservation connects the most personal human experiences, watching a figure skater's graceful spin, to the most cosmic phenomena, the formation of galaxies and black holes. Every time you see someone spin up by pulling in their arms, you're witnessing the same fundamental principle that shaped the universe itself. The conservation law that makes a child's top keep spinning is the same law that keeps galaxies rotating and determines the behavior of matter at the quantum scale. The next time you watch figure skating, remember that you're not just seeing athletic artistry, you're observing one of the universe's most fundamental principles in action. The skater isn't creating energy from nothing or violating any physical laws. They're demonstrating how Emmy Noether's insights about symmetry and conservation play out in the real world, showing us that the universe maintains perfect mathematical accounts of every rotation, every spin, every angular motion that has ever occurred. In the elegant pirouette of a figure skater, we glimpse the mathematical precision with which the cosmos keeps track of its own motion, ensuring that the total angular momentum of the universe remains forever constant, a cosmic legacy of the rotational symmetries that have governed matter and energy since the beginning of time itself.